The previous video cut off 3 minutes into a 26-minute video. It's getting very late, so I'm going to have to go through this kind of quickly. And I apologize for that, but either my voice or my brain is going to shut down here before too long. Okay, we're verifying Stokes' theorem for this function on this region. We've established that the plane region is x plus y over 2 plus z over 3 equals 1, which I believe is correct. If we plug 1, 0, 0 in, 1, 0, 0 gives us 1. 0, 2, 0, 0 here, 2 over 2 is 1, and 0 here, etc. Alternatively, well, let's not worry about alternatives right now. Okay, so this being the plane region, this is a level surface for this function, so that the normal vector is going to be the gradient of that function, I plus 1/2 j plus 1/3 k. Now this is a normal vector. It's not the unit normal vector that we need to use in Stokes' theorem. So to find the unit normal, we divide the normal by its magnitude. And conveniently, the magnitude of this vector turns out to be the square root of 49, 6 squared plus 3 squared plus 2 squared, 36 plus 9 plus 4 is 49, the square root of which is 7, so we don't have radicals to worry about. So that our quantity curl of f dot n is just curl of f, which is z squared j plus 2k, dotted with n, which is our 6i plus 3j plus 2k over 7. And we see that we have 0i component. We have z squared for the j component, so it's going to be z squared times j dotted with 3j over 7. Giving us 3z squared over 7, and 2k dotted with 2k over 7, which is going to give us 4 over 7. And we get a very simple expression for our curl of f dot n. Now, it's not going to stay that simple because, remember, we're probably going to want to integrate this over the region in the xy plane, so we want to express z in terms of x and y before we complete our expression for curl of f dot n. In other words, we want this to be in terms of x and y so it can be integrated with an xy region. Solving this equation for z, very straightforward. Factoring out a 1/2, you can verify that if you multiply this through, you get this, so you can work backwards and see how I factored out the 1/2. And then substituting this expression in for z, we're going to have to square this. You can't use FOIL to do that. You have to use a distributive law, and you have to write it out carefully. And if you do, you probably end up with something a little better than what I did, because here's where my error occurred. This is 3z squared plus 4 over 7. What I wrote down was essentially just z squared plus 4 over 7. I didn't write out 3z squared over 4 plus 7. So we want to figure out what's the integral over the surface of curl f dot n with respect to surface area. And this region is fairly simple. The region just projects into the plane, again, to the triangle with vertices 1, 0, 0, 0, 2, 0, 0, 0, 0. Sketching that triangle and reorienting the x and the y axes to the traditional orientation for the two-dimensional sketch, we have the point 0, 2, 0 represented here, 1, 0, 0 represented here. Remembering that the third coordinate 0 is the z-coordinate, and we're talking about the xy plane. So that the boundary of this region, well, we have a lower boundary, we have a boundary on the left, but the boundary here is y equals 2 minus 2x. And it's very straightforward, slope-intercept form, with z equal to 0. So that our region of the xy plane is 0 less than or equal to x less than or equal to 1, 0 less than or equal to y less than or equal to 2 minus 2x. Now to do the surface integral. Well, I've made a pretty clumsy sketch. I made the sketch too small so that my area increment here came out way too small. So let's just take a look at a bigger picture. Here's a bigger picture. We have an area increment delta Aij, a delta x by delta y increment in the xy plane, with sample point xi star, yj star. And above that increment we have a surface area increment, delta Sij, and the area of this increment turns out 7/2 the area of this increment. Now we get that 7/2 because n is going to be evaluated at xi star, yj star. Our normal vector n was 6i plus 3j plus 2k over 7. If we dot that with k, we get 2/7, and n dot k is the cosine of the angle gamma, which is going to divide into the Aij to give us the delta Sij, and that's going to give us a 7/2 delta x delta y. And we can see in more detail, I've written out the delta Sij is the delta Iaj divided by n dot k being 2/7. We divide delta Aij by 2/7, getting 7/2 of delta Ij. And just for reference on familiar territory, if we want to find the surface area of this triangle, we simply integrate over our region where x goes from 0 to 1, y goes from 0 to 2 minus 2x, and we integrate the delta Aij, the 7/2, which becomes a dy dx with this order of integration. It's a very straightforward integral. We get 7/2. That's exactly what we would expect to get, because surface area of any increment on the surface is 7/2 as great as the surface area of the projection of that increment onto the xy plane. So that the 7/2 will apply to any area increment, and this triangle therefore has 7/2 the area of the triangle in the plane, and the triangle in the plane is base 1, altitude 2, has area 1, so that the 7/2 appears to hold.